Given that p is a positive constant, show that the sum from 1 to 11 of ln p to the power n is equal to k ln p, where k is a constant to be found. So this is saying to substitute 1 into the rule. So I've got ln p to the power 1, then substitute 2. So ln p to the power 2, then substitute 3, ln p to the power 3, then 4, and so on, up to 11. Now, in each of these terms, I can use the law of logarithms to move that power to the front. And now I notice that this is an arithmetic sequence that's going up by ln p each time. We've got first term, which is ln p, common difference of ln p, and there are 11 terms in this sequence. So using the sum formula for this, got n over 2 times 2a plus n minus 1 times d which gives 66 ln p. So that's my answer for the first part of this question. Part B says to show that the sum from 1 to 11 of ln 8p to the power n is 33 ln 2p squared. So this is part B of the question. I'm noticing this is very similar to what we've just done, but I can't see how to use it directly just yet. So again, let me just write out the first few terms of this sum. So first, when n is 1, we'll get ln 8p to the power 1. Then when n is 2, then when n is 3 and 4, all the way up to when n is 11. Now, one thing I note here then is I could actually use the laws of logarithms to split each of these terms up. The ln 8p, I could write that as ln 8 plus ln p. The ln 8p squared, I could split that up to be ln 8 plus ln p squared. And so on. So again, just to be super clear, splitting this up using the addition law to be this. Splitting this up with the addition law to be this. And so on. Now, what we have here is I've got ln 8. Remember, that's just a constant. I've got 11 of those because there's 11 terms in this sequence. So that's just 11 ln 8. And then all of the other terms is the same as what I did in part A. So plus the 66 ln p that I did in part A of this question. All I need to do now is to try to make that look like this. 33 ln 2p squared. Well, the the 8 here, I can think of that as being 2 cubed. And then I can bring that 3 to the front to be 33 ln2. Plus the 66 lnp. I could factorise 33 outside. And then I'm actually going to take that 2 and move that to be a power here. So that I can then combine those two logarithms together to be 2p squared. And that's what we needed to show for part B. And then finally, part C. Hence, so using what we just did, find the set of values of p for which the sum from 1 to 11 of ln 8p to the power n is less than or equal to 0, giving our answer in set notation. So we've just shown that this is the same thing as 33 ln 2p squared. So when is that less than 0? Well, we can divide both sides by the 33, so we'll get ln 2p squared is less than 0. Now, let's think, when do we get a negative with a logarithm? Well, it's when we do ln of a number. Think about the log graph. When we do logarithms of numbers that are less than 1, of numbers between 1 and 0. So if this 2p squared is less than 1 but bigger than 0, that is where ln 2p squared will be negative. Dividing through by 2, so p squared would have to be greater than 0 or less than 1/2. And square rooting, so if p is between 0 and 1 over root 2, now I do need to give this in terms of set notation. So the set of numbers of p such that p is greater than 0 but less than 1 over root 2. And there we go.